Black holes, they are without a doubt one of the absolute strangest things in all of existence. I mean, they're these places where the laws of physics, everything we think we know, just seem to break. So let's try to piece together the life story of these cosmic monsters. We're going to tackle the really big questions. We'll trace the entire life of a black hole, right from its incredibly violent birth all the way to its impossibly slow death. And yeah, of course, we're going to explore that ultimate question. What would it actually be like to fall into one? All right, so where do these things even come from? Well, their story, kind of paradoxically, doesn't start with darkness at all. It starts with one of the most brilliant and violent events the cosmos has to offer, the death of a truly massive star. So for most of its life, a giant star is in this constant, stable tug of war, you know? You've got nuclear fusion pushing everything out, while its own immense gravity is trying to crush everything in. But eventually, that star creates an iron core. And with iron, fusion just stops. Suddenly, gravity wins. The entire star implodes at a quarter of the speed of light, then rebounds in the spectacular explosion we call a supernova. This explosion is actually how the universe gets seeded with heavy elements, the very stuff that eventually makes up planets and, well, even us. And what's left behind in the rubble? A brand new black hole. Okay, our black hole is born. But what is this thing, really? Let's peel back the layers and take a look at its truly bizarre anatomy. So this is the black part of the black hole. The event horizon isn't some kind of physical surface you could touch. It's a boundary. It's the point of no return. Once you cross it, there is no coming back. To get out, you'd literally have to break the ultimate speed limit of the universe, the speed of light. And since that's impossible, nothing escapes, not even light itself. Okay, so this is a really crucial point. Black holes don't suck. They're not cosmic vacuum cleaners roaming around gobbling things up. They just have an immense amount of gravity because they've packed so much mass into such a tiny space. I mean, if our sun were to magically be replaced by a black hole with the exact same mass, guess what? Earth would just keep on orbiting it perfectly fine. We'd just, freeze to death. And deep down at the very center, that's where we find the hole in the black hole, the singularity. This is where all the matter from that original giant star is theoretically crushed down into a single point with zero volume and infinite density. The problem is we really just don't know what a singularity truly is. Our current laws of physics completely break down when we even try to describe it. It's like the universe is giving us a dividing by zero error message in our own rulebook. All right, now for the part I know you've been waiting for. Let's put ourselves in the picture. Imagine you're an astronaut on the universe's most dangerous mission. What would you actually experience? This is where reality just gets completely weird. It's like something straight out of science fiction, but it's real. To your crewmates watching you from a safe distance, you just appear to slow down. You'd get redder and dimmer until you seem to just freeze in place, stuck on the edge of the event horizon for all eternity. But from your perspective, you'd watch the entire future of the universe flash before your very eyes. So once you cross that point of no return, your journey probably ends in one of two ways. The first has a fantastic name, spaghettification. The black hole's gravity would pull on your feet so much more powerfully than on your head that you'd be stretched and stretched and stretched into a hot stream of plasma, just one atom wide. The second theory is even quicker, but no less terrifying. Some physicists think the event horizon isn't empty space at all, but a firewall made of high-energy particles. The moment you cross it, you wouldn't even have time to be stretched. You'd just hit this wall and be instantly vaporized. Now, which of those horrible fates you'd suffer? Well, it actually depends on the size of the black hole. And as it turns out, they are not all created equal. They come in a whole variety of cosmic sizes. We've basically found two main types. You have your stellar mass black holes, which are born from a single star. They're only a few times the mass of our sun. But then you have the supermassive ones. These monsters lurk at the center of nearly every galaxy, including our own Milky Way, and they have masses millions or even billions of times greater. So, to give you some sense of scale, the current record holder for the biggest black hole we've ever found has a mass equal to 40 billion of our suns. That's a number so huge it's almost impossible to even wrap your head around. And what does that mean for its actual physical size? Well, its diameter is 47 times the distance from our sun all the way out to Pluto. Think about that. Our entire solar system would just be a tiny little fraction of its width. It is a true cosmic leviathan. You might think they're eternal, these cosmic monsters, but it turns out even black holes have a lifespan. So let's talk about the final quiet chapter in their story, an incredibly slow fade into absolutely nothing. It all happens through a process called Hawking radiation. You see, it turns out empty space isn't really empty. It's constantly fizzing with pairs of virtual particles that pop into existence and then immediately cancel each other out. But if this happens right on the edge of a black hole, one particle can fall in while the other one escapes, and that escaping particle carries away a tiny, tiny bit of the black hole's mass with it. Now, this whole process is unbelievably slow, but it gets faster and faster as the black hole shrinks. When it's down to the mass of an asteroid, it's just radiating at about room temperature. By the time it has the mass of a mountain, it's blazing with the heat of our sun. And in its final, ultimate second, it detonates with the energy of billions of nuclear bombs. So just how long does all of this take? Well, for the largest supermassive black holes, it could take a Google years. That's a 1 followed by 100 zeros. It's a timescale so vast it makes the entire current age of the universe seem like less than the blink of an eye. Which leaves us with one final, kind of haunting thought. In that impossibly distant, dark future, long after the last stars have burned out and the galaxies have all faded away, the final fireworks in the cosmos will be the explosions of these evaporating black holes. And when the very last one is finally gone, what, if anything, will be left?